Here's our definition of irreducible operators or tensors or irreducible tensor operators. They transform like this. We see an irrep here, and then we have this funny conjugation with this representation living on the same space on which these operators act. So let's convince ourselves first that this really makes sense, that this here really defines a representation of our group on the space of linear operators. So let's look at this. U of GH, O mu I, U of GH inverse. So we just replaced the G by a GH, so we should just get the right hand side with the GH here, and if this is all consistent, this should also work if we subsequently transform with G and then with H. So let's check if this is true. Here we have U of G, U of H, O mu I, and now here we have U of G times U of H and the inverse of that, so we get a U of H, hopla, H inverse U of G inverse here. Now this here is just an instance of this relation. So let's use this. We copy the U of G, and then we write sum J from 1 to D mu, O mu J, gamma mu of H, Ji, and then we have to copy the U of G inverse here. Now we can do this again. There's the conjugation with the U's, and here is the O mu J this time. So we get a double sum now. Let's say sum J and K from 1 to D mu. Just copy the O mu J. No, we shouldn't. We get an O mu K, gamma mu of G, K, J, and then we copy the gamma mu of H, Gi. So the orange part led to this here now. Okay, but now this is all fine, because the index J here meets the index J here, and there's a sum over J. So this is really just a matrix product, and we get the matrix element Ki of this matrix. So let's write this down. This is sum over K from 1 to D mu, O mu K, and now we have the matrix gamma mu of G, the matrix gamma mu of H, and let's say matrix element Ki I of that. But the gammas are a representation, an irrep, so we really have sum K from 1 to D mu, O mu K, gamma mu of G H, matrix element Ki, and that's where we want it to end up.